in the way. So I just skipped that section. Anyway, 13.3 is about partial derivatives. And 13.4, it says differentials. I would have called it increments in differentials. But anyway, that's where you get all this kind of information. They don't present it exactly the same way I do. And I'm going to maybe work the problem or two the way they do it. But the thing is, we're not going to spend a lot of time on this section anyway. So I'm slanting this towards the things that point towards the theory in section 5, the chain. All right. But I will come back and do more with this, particularly when I remember to put that supplement out there. So I have a supplement on differentials. Print that out and bring it next time. And the kinds of things I have on that supplement are like uses for differentials. The differentials are used for error analysis. You know, if I make a mistake, if the maximum error for the length of a box is 0.17 and the maximum error for the width of the box is 0.23 and the maximum for the height of the box is whatever, then what's the maximum possible error in the volume? Or what's the maximum possible error in the surface area? Sometimes I have to say error and area in the same sentence, and it sometimes troubles. Well, anyway, so I'm going to talk about that stuff next time. But for now, I want to just leave the rest of 13.4. These are the only formulas I need right now. There's an interesting formula or two in here that I will get to, but I don't use it in going to the chain rule. So anyway, 12.5 is the chain rule. And I like to just make a brief start on the chain rule. And it'll only be a brief start because I want to start by reviewing the Cal 1 chain rule. Just like a while ago, I reviewed Cal 1 differentials and increments. Concentrating on, cherry picking the things I wanted to emphasize here. Well, anyway, so let's review chain rule just a little bit. What is the chain rule about, ultimately? The derivative of what kind of function? What? Well, that could be a possibility. So if I've got, say, I have x to the 5th, well, that derivative is nothing to it. That's just 5x to the 4th. I don't need a chain rule for that. But if I'm looking at a 5th power of some other weird thing, like x cubed plus the sine of 3x, then I need the chain rule. We're taking one function and doing a power of it. But it doesn't have to be a power function combined with another function. It could be any function combined with another function. What do you call that kind of combination of two functions? What? Oh, well, okay. Some of them are polynomials. So this one wouldn't be a polynomial. I'm going to think of this function here, the 5th power function. Let's call that one f of u equals u to the 5th. And then this other function, I'll call it g of x. It's what? Composition of functions. The chain rule is the formula for finding the derivative of a composition of functions. That's exactly what it is. And so, how does it work? So abstractly, Now, if I wanted to work this one out and I did not know the chain rule, or I didn't know the power rule with the u prime in it, then I would say, okay, I've got one function, and I'm going to call it f of u. Let that be y. And then the u is some other function, g of x. In college algebra and pre-cal and pre-cal is a good term for it. Pre-calculus mathematics, and that includes algebra and arithmetic and geometry and all that mess. But in pre-calculus mathematics, a lot of times they'll write things like this: f of x is x squared plus 7x minus 2. G of x is 3x plus 4. And they want you to find f compose g of x. Maybe g compose f of x for that matter. And so, anyway, what we have to do, okay, that's f of g of x, right? And g of x is 3x plus 4. And so then I have to do f of 3x plus 4. Wait a minute, it's supposed to be f of x. It's not supposed to be f of some other combination with x. But we just say, okay, instead of x squared, I'm going to do that thing squared. In calculus, we're much more apt to use different letters for it. This is more logical. There are times when we need this facility in letting things slide. Okay, over here x means this, but now I'm going to let x mean something else. And there's some important things for that. But we don't need that in college algebra. I don't know why these books can't get that straight. So anyway, I'm going to use a different letter for the output of G than I use for the output of F. I'm going to use a different letter for the input of G than I'm going to use for the input of F. Having said all that, we would have y equals f of g of x. So that's y equals, yeah. So the u is g of x. And then I'm going to rewrite that using the symbolism, the fog symbolism. And I think for a lot of college algebra students, it's the foggy concept, very well notated there. All right, so that's what's happening. And so over here, g of x is x cubed plus sine 3x, and f of u is u to the fifth. And then I'm going to replace the u, the base here, with that thing. All right, so how does it work? What's the formula for f circle g prime of x? How many of you remember this one?
It's
Nobody?
f of g of x.
There we go. Okay, I'm impressed. A lot of times I can ask this question and nobody will admit to knowing it. That's right? Yeah, that's right. The proof of this is kind of tricky, but luckily I don't prove much in calculus courses. But I can give you a plausibility argument for this. I can show you why this works. And here's the deal. This notation with the primes, that's called Lagrange notation. Later on in the chapter, they've got, what's it called? Can't remember the name of it now, but Lagrange shows up later in the remainder. Well, yeah, that's for Taylor series. No, later on when we're doing max-min theory for functions of several variables, it's Lagrange multipliers, that's what it is. But anyway, same Lagrange. But anyway, he's one of the first ones that used f of x a whole lot, and the primes. The other notation is Leibniz notation, with the d's and the del's and all that stuff. It's easier to understand the chain rule in Leibniz notation. So, we look at this here. We say, all right. We started out a while ago with f of x. And the Leibniz notation for f prime of x, this is the Lagrange notation, but the Leibniz notation was dy dx. So, we got a different situation here. U equals g of x. So the derivative g prime of x would be called what?
Du.
Du? The differential? No.
Du over dx.
D over dx. All right. And we have that y equals f of u. So f prime of u would be
dy over dx.
dy over dx. Okay. And we have f circle g of x. Now, what was that one? F circle g of x is the y. So f circle g prime of x would be what?
We just wrote it down.
Well,
Next to your head.
yeah, no, okay, but all right, work with me here. I'm trying to build up an analogy with all these D things. Say it with D's. Don't say it with flowers. Say it with D's.
dy over dx.
dy over dx. And again, a lot of times when we use the chain rule, for the purposes it's used for in Calculus 1, we're just calculating some function, and maybe we're even calling this thing f of x. We don't, because, you know, they have a page of derivatives. Here's f of x equals blah, find f prime of x. And then the next problem, here's another f of x, find f prime of x, etc. So f is often our name of these functions, but in analyzing it, I need this function composed with the other function, and it's customary to use f and g for those purposes. A lot of semesters, and I forgot to do it this semester, a lot of semesters I'll say I want this one to be called f, and I'm going to make it the composition of g and h. Wish I'd done that, but I'm already too far down this road and it's too close to the end of the class for me to switch over now. Maybe next week I'll start doing that. But anyway, so here goes. Yeah, I wish I had done it that way. I've been doing that several semesters, and I just didn't think about it this time. All right, but anyway, so equals big old question mark, because only one person admitted to knowing what the formula was. Out loud, anyway. And I'm not a clairvoyant. So anyway, what is f circle g prime of x equals dy dx. And here's the things I got to work with. The du dx and the dy du. Oh, wait a minute. If I just multiply those. Oh, so this is dy du times du dx. That's the way fractions work. And then what was dy du? Dy du was f prime of u. And this other one was g prime of x. And so this is the chain rule formula in Leibniz notation. Nothing can be simpler. Here's basically the chain rule formula in the Lagrange notation. But we don't usually leave it that way. We usually say, well, we want it all in terms of x, don't we? So let's see, the u is g of x. So then we plug in and write f prime of g of x times g prime of x. And so there's our chain rule in Lagrange notation. And sometimes I think of it as Lagrange notation. And when we get into several variables here, it's really grungy. This one gets grungy also, but not as bad as this does. Okay, so that's my review of the chain rule in Calculus 1. And I think I'll just plunge into Calculus 2 now. Too bad that this is a Thursday and it's 5 more days till the next class meeting. I wish it were just around the corner, so to speak, but anyhow, this is very much going to be a to be continued situation. Anyway, so here goes. Remember, one more thing here. I like to write it this way. X, and I'm going to use an arrow for mapping for my function. X generates the u, which generates the y. So this is my g and this is my f. This is kind of an imitation of advanced mathematics diagrams. But anyway, I call this a variable scheme. And if you know the variable scheme, you can write down the chain rule for it. The book uses a different variable scheme. Instead of doing this horizontally, they do it vertically. And it becomes a real mess when they go to several variables. And first of all, they also try to make it fancy and they'll put a circle around here and they shade it in pink or something like that. But anyway, well, I don't do that. So, I've got an independent variable and a dependent variable. And then there's this other variable. And as far as the f function is concerned, that u is an independent variable. But as far as the g function is concerned, the u is a dependent variable. It just can't make up its mind. So I'm going to make it up for it. I don't call it either one. This is an intermediate variable. So x, independent variable. The u is the intermediate variable, and the y is the dependent variable. And look what happens in the Leibniz notation of the chain rule. The dependent variable is always on top, the independent variable is always on the bottom, and the intermediate variable is sometimes top and sometimes bottom. And that's the way you can keep some of these things straight. And anyway, so now, what did I say in the first night about the distinction between Cal 3 and Cal 1, or in Cal 3 and Cal 2? It was
Less
one.
integrals?
What now?
Less integrals?
There was a cough. What was it?
Less integrals?
Less integrals. Oh, well, is that really true? Does Cal 3 have less integrals? I mean, I know I'm just getting started on the integral chapter, but I would think that you would say, oh, he's really going to town on those integrals. Let's see, one of the distinctions was vectors, and one of the distinctions was we do a lot of three-dimensional space stuff.
And definite integrals.
And definite intervals. Oh, that's right. Okay. We do a lot more with definite intervals in Cal 3 than indefinite intervals, whereas in Cal 1 and Cal 2 we did. I never thought of that as the main difference before, but you're certainly right. And anyway, The other distinction that I make is the kinds of functions we have. In Cal 1 and Cal 2, we're only doing functions of how many independent variables?
One.
One. How many dependents?
One.
All right, and in Cal 3, in chapter 12, we had one independent and more than one dependent. In chapter 13, and now in chapter 14, with the intervals, the definite intervals, we've got more than one independent and just one dependent. And in chapter 15, the kitchen sink chapter, we're going to have more than one independent and more than one dependent. But what about the chain rule? Now I've got a third category of variables. So guess what? For the chain rule in Cal 3, we can have more than one independent, or more than one intermediate, or more than one dependent, or more than one of each of these, more than one of each of these, or more than one of each of these, or more than one of everything. It's just crazy. But the toughest part, the step that is the most unusual is going from going from one intermediate to more than one intermediate. So that's the one I'm going to concentrate on. So with that in mind, I'm going to work it out for this variable scheme. T is going to map to x and y and map to z. So here's the deal. Z is going to be a function of two variables. F of xy equals z. I like to get that in there because I've done a lot of the Cal 3, the chapter 13 stuff with this setup. And I could say that xy is g of t, but that's not the way I'm going to do it. I'm going to separate them. I'm going to say that x is going to be one function of t, and I don't want to go with g and h here, so I'm going to say g1 and g2. But in a full-blown linear algebra-based treatment of this, it would be xy together. It would be two variables here with one variable there. It would be just one function with two dependent variables. All right, so anyway, that's the setup we're looking at. So, z is f of xy, but x is g1 of t, and y is g2 of t. So that's what we're after here. So the chain rule for this variable scheme, and very much it's going to be a chain rule for this variable scheme, there's a different chain rule for that variable scheme. For each variable scheme, you can write down a chain rule for it. But anyway, for this variable scheme, we're concerned with the chain rule is a rule for finding the derivative of this kind of a composition. Do we want to write it as a composition? We could. F composed with the pair of functions g1, g2 of t. All right? But don't think about it that way. That's all. All right. So, how am I going to get the chain rule? Here goes. Looking at this, do I still have the formula for differentials up here somewhere in some form? Well, not really. I'm going to write down the formula for differentials. So dz equals what? So if z equals f of xy, then what's dz?
F sub x.
Well, say it with del's.
Del,
Which one goes on top?
Del f over del x.
Or, okay, del f over del x. But I like to say it with the variables instead of the function names. So del what?
Del Z.
Del z times
dx.
dx. And now you're on a roll again, I bet.
Plus del Z.
Right.
Over del y.
All right, so there is my formula for differentials. I'm going to start with the formula for differentials. And what I want is dz dt, right? The composition, z is a really horrible, stupid function of t. One independent variable, one dependent variable. And so, in the horrible Lagrange notation, we would be writing this. But in the Leibniz notation, my stand-in for the function is the dependent variable z, and then the independent variable is t. So I want dz dt. And I've got dz. So guess what?
Just divide
Still like
everything.
Divide
Still
everything by
zero.
dt.
So it's
And that's okay, because this really is division. Partial derivatives are not really division, except in limited, and that's not fun, limited circumstances. Very good. All right, and you were about to tell me how I could rearrange this, I bet. So if I just look at this term, if I divide that thing by dt, there's a nice little place for the dt.
dx dt.
Dx dt. So dz dt equals del z del x times dx dt. And that takes care of the first term. And then I'm going to have the other one, del z del y dy dt. Good thing I wrote those with different notations, with del's and d's. Otherwise, I'd be tempted to cancel them, and then I'd have dz dt plus dz dt is 2 dz dt, which wouldn't look very good here if I were writing them all as d's. And it would be wrong. Okay, so I won't get much further than that because I'm almost out of time. I got a minute. But I could go ahead and write down one example and just see sort of what we get. I really wanted to at least do an example. So I'll make it an easy example. Let's have x equals about sine t, and y equals t e to the t, and let's have z equal, I don't know, how about x squared plus y squared or something like that. Then del z del x, del t, dz dt's, no, del z del x. So del z del x is, say, 2x. Del z del y is
2y.
2y. Dx dt and dy dt.
It's just the derivative of x plus the derivative of y with respect to t.
Derivative of x.
Yeah, we have a function that's x equals sine t.
Yeah. So I'm just taking the standard Cal 1 derivative. And this one, oh, stupid product rule, t plus 1 times e to the t. So when I take the derivative of e to the t, I get t times e to the t. When I take the derivative of t, I get 1 times e to the t. So there it is. All right, so putting this together, I've got del z del x, dx dt, plus del z del y, dy dt, equals 2x times cosine t plus 2y times t plus 1 times e to the t. And you know they never let you leave it that way in Cal 1. You always got to take it all the way to the independent variable. So this will be x was sine t. So this will be 2 sine t cosine t plus 2y, y is t e to the t. 2t e to the t times t plus 1 times e to the t. Well, yuck, I can simplify that. So 2t squared plus t e to the power 2t, right? Okay, bear with me a little bit, I'm gonna do one more thing here. I wanna check it. So this is supposed to be dz dt. All right? How can I check that? Take the t derivative of z, how?
Substitute x and y.
Substitute first. As long as I got a substitute at the end anyway, why don't I substitute from the get-go? So z is actually equal to sine squared t plus t squared e to the 2t, right? I'm just squaring that thing. And so now, oh, sine squared, of course, you get 2 sine t cosine t. dz dt equals, well, I haven't looked at that one yet, but guess what? It's going to be that. Okay? Now, what good is the chain rule? If it's easier to just go ahead and plug that in and do a little product rule there, and a little power rule there, why did we go to all this trouble? And yeah,
Because it's not gonna be
You got it
repeated.
right?
what?
Make sure you got it right.
Well, no, but I mean, if I wanted to be, which looks more reliable? This or that? I think this looks more reliable. This is more natural. But
Maybe
why
so.
do we do this? What?
What if z is really ugly?
What is Z is what?
Maybe z is really ugly.
Well, yeah, but that's not really it. And of course, come back next time and we'll see. But the thing is that we don't use the chain rule this way when we have complete information. Ugly or not, if we've got complete information, we're just gonna substitute and go with it. But what happens a lot of times, and I wish I had time to give you an example, maybe we know all about this, but we don't know that one. Or maybe we know all about this one, but we don't know about that one. We're working with incomplete information, and that's where the chain rule shines. Anyway, trespass on your time, all of that.